First, let's do an example of the type of problem that we just theorized. This says find the volume, and it's going to be a find the volume problem. I just left out those words for all of these in this section. But the region between these curves, x equal to 0, that's a vertical line, f of x equals y equals 3x plus 1, straight line, x equal to 2, vertical line, and g of x equals y equals the square root of x, a curve, rotated around the x-axis. So this is the type of problem that we just talked about. It's a type 1. There's a picture of the type 1 area from 0 to 2. And on the left, or the picture on the right is the picture of the area, and on the left there's what it looks like when you rotate it around the x-axis. So those vertical slices, since it's type 1, are going to turn into washers. And now we need to figure out what are the big radius and the small radius. The big radius is the top function because it's further away from the x-axis, and the small radius is the square root of x. It's closer to the x-axis. So here's the setup. The volume is the integral from 0 to 2 of pi times the big radius squared, so that needs to be in parentheses to square the whole thing, minus, and then parentheses, the smaller radius, square root of x squared. And then you can simplify and integrate. You have to do FOIL on those parentheses in the first part, and that's where I got the 9x squared plus 6x plus 1. Square root of x squared cancels out, and I get an x, and that minus comes after the squaring, so minus x. And then the antiderivative here is real easy. I'll let you do that. It's raise and divide on all those pieces, and put again the 2 and the 0. Don't forget the pi. I did pull that pi out front of the integral, which is fine, or you can leave it inside, it won't matter. It's a multiplier, and so you'll get 36 pi. Inches cubed, it's a volume, although you can leave off the units. I just put it on there to remind you that you're finding a volume. Alright, so let's look at type 2. Now, the same setup occurs, or I should say a similar setup occurs, when you rotate a type 2 area, type 2 region, around the y-axis. So here's a type 2 region. It has f on the right, g on the left. You can slice it into horizontal slices. And when you rotate it around the y-axis, I didn't attempt to draw the whole picture this time, I just drew the washer. Because when you rotate that horizontal slice around the y-axis, you get another washer. It has a thickness this time, which is dy. And it has two radiuses. The bigger radius is going to be the function that's further away from the y-axis, that's f of y, and the small radius is going to be the one that's closer to the axis of rotation, that's g of y. So the volume will be the integral from the low point to the high point, since they're y values, of, and this is pi r squared minus pi r squared again for the two radiuses. But at this time it's pi times the big function squared, the further one to the right squared, minus the one that's closer to the axis of rotation squared. And I'll do an example of those. Alright, so this example is to find the volume again, and we're supposed to find the volume of the region between y equals 1 and y equals 3. Those are horizontal lines. And between the functions x equal to y and x equal to 2y, those are straight lines, rotated around the y-axis. So on the left there I drew a little picture of the region so that you can see it is type 2. It needs horizontal slices. And I was nice on this problem, already have solved the functions for x so that they're functions of y, x equal to y and x equal to 2y. That means we can think about the washer of a slice, a horizontal slice that gets rotated around in the big picture. You can picture it being a stack of washers. The book has some nice pictures where they show you stacks of washers for these problems. And here's the setup. Since it's a washer, it will be the integral. Oh, there's a missing 1, didn't photograph well there, but in the second integral you can see it. Integral from 1 to 3, since those are the low point and the high point. Pi times 2y squared, that's the furthest to the right, the bigger radius, minus the y squared. And then we can pretty quickly work out the antiderivative there. I just combined 4y squared minus 3y squared to get, or 4y squared minus y squared to get 3y squared. And then raise and divide that, gives you y cubed. And then plug in the 3 and the 1, gives you 27 minus 1, so the answer is 26 pi.